the equivalent circuitry for a logic circuitry for a binary cell that stores 1 bit of information can be like this. So, this is as I said that this is just an equivalent circuitry. So, actual RAM cells are not like that. So, in that case I told you that individual SRAM cells they require only 6 transistors, but here you see that I have put an SR flip flop. So, SR flip flop means you have got some 4 NAND gates. Okay. So, 4 NAND gate, each NAND gate takes 4 transistors. So, that will take 16 transistors. So, this SR flip flop itself will take 16 transistors, then we have got all these AND gates and etcetera, inverters etcetera, they will take more number of transistors. So, this is just a logical diagram, do not take it as the actual memory diagram, but from the digital logic point of view. So, this is an equivalency of equivalent of what is happening in the memory cell. So, the equivalent logic of a binary cell that stores 1 bit of information is like this, that if read write bar is equal to 0, then it will select and select equal to 1, then the input data is put into the SR latch. So, input is coming. So, if read write bar is 0, that means we are trying to do a write operation. The select line is actually the enable line of the memory chip, you can say. So, at this location I am trying to write the value. So, whatever is coming at the input they should be stored here. So, if you look into this diagram, so when when this read write is equal to 0, read write bar is equal to 0. So, this line, so this AND gate, so it has got this select equal to 1, this read write bar equal to 1, and input is whatever be the input value that will be coming here. And you see, since this read write bar line is equal to 0, okay. So, since this is equal to 0, so this will be coming as this will be coming here. So, this will be coming as 1 here, and the input bar will be coming to this point, this reset point. So, in the S I have got input, and in the R I have got input bar. So, as a result, whatever be the value of the input, that will get stored here. So, if input value is equal to 1, in that case I have got S equal to 1 and R equal to 0. As a result, this flip flop will be set to 1. On the other hand, if input value is equal to 0, then I will get here S equal to 0 and R equal to 1. As a result, the value of this Q output will be equal to 0. So, this way this value input is getting stored in this SR latch, and then for the output part. So, we have got this if the select line is 1, then whatever be the output, that will go to whatever be the out flip flop value here, the latch value here. So, that will come to the output, provided this read line is made equal to 1. So, that is the read operation. So, conceptually we can say that if this is the basic cell, so this whole thing is the basic cell. So, it has got the inputs like select, input, read write and output, the output line as output. So, that way this cell works. Of course, you should as I have already said that this is just a logical diagram, not the physical one. Now, how can we construct a memory array? So, I have talked about in the previous slide the design of this basic cell or BC. Now, if you are suppose we are trying to construct a 4 by 4 RAM, that is there will be 4 locations or 4 address locations, and each location is consisting of 4 bits. So, I take 4 by 4, that is 16 basic cells arranged in a 4 by 4 fashion, and then there is so this address line. So, since there are 4 such memory locations, so I will need 2 address lines. So, 2 address lines are coming here. So, and I use a 2 to 4 decoder. So, this memory enable line is connected to the enable line of the decoder. So, if this memory enable is equal to 0, if this memory enable is equal to 0, as a then all these decoders, all these outputs will be 0. So, none of them will be, none of the location values will be available at the output. On the other hand, if enable equal to 1, so depending upon these address lines, depending upon this, if enable is equal to 1, so depending upon these address lines, so one of these word lines will be selected. Suppose for example, if the address line is say 0 1, then what will happen? So, this will be 0, this will be 1, this will be 0 and this will be 0. So, the content of this basic 4 basic cells, so they will be available here. Okay. So, the otherwise since the select line is 0, so will be so this BC lines will be these basic cells outputs will be 0. So, they are these basic cell outputs in column wise. So, they are odd at this point. So, then you get the 4 bit output data. So, we need some sort of decoding circuitry from the address lines to select the appropriate row of this array, and then these individual columns of this array. So, they are odd to produce the individual the output part of from the chip, and for the input part. So, they will be connected here. So, they will come to the basic cell. So, there is a need for decoding the circuit, there is a need for decoding circuits to select the memory word specified by the input address. During the read operation, the 4 bits of the selected word go through the OR gates to the output terminals, as I explained, and during the write operation, the data available on the input lines, that is these points. So, they will be available on the input lines and the transfer to the 4 binary cells that we have selected, and then so that way the whatever input data will be coming and whatever address line are given. So, based on that, a particular row will get selected and this input data value will be stored in those binary cells. So, a memory with 2 to the power k words of n bits per word will require k address lines, and that will go to k by 2 to the power k decoder. So, this decoding circuitry becomes a major concern, because if you are having a large sized memory, so you have got a large number of rows in that memory, and so this decoder has to have so many outputs. So, this is a simple 2 to 4 decoder when we have got say 4 memory words. So, if there are 1 kilobyte of 1 kilo memory word, then this decoder size should be 10 by 2 to the power 10. Okay. So, that way it will go on increasing significantly, exponentially the requirement of the decoder will go on. So, that is a major concern. So, to reduce the complexity of this decoder to some extent, so what is done? We have got some structure which is known as coincident decoding. So, this coincident decoding is like this. So, a decoder with k inputs and 2 to the power k outputs require 2 to the power k AND gates and k inputs per gate. So, this is the standard design of the decoder that we have seen previously. The 2 decoding in a 2 dimensional selection scheme can reduce the number of inputs per gate. So, so in this particular case, suppose I have got a memory array that has got 1 kilo word of memory. So, 1 kilo word of memory, so that is there are 1024 locations. So, 1 kilo word means there are 1024 locations. So, if you are thinking about a simple design, then I should have a decoder like this that has got 10 number of inputs and this 1024 number of outputs. So, individual outputs going to individual arrays, individual rows of that cell array. However, you can do it like this. So, you can divide these 10 lines into row address and column address part. So, first you put this so this x and y are divided 5 bit they are divided, and then so put a 5 by 32 decoder. So, it selects this one of these 32 locations, one of these 32 rows, and then we have got a 5 by 32 decoder on the column side that will select again 5 by 32 5 by that will again select one of the 32 columns. So, this is the 2 dimensional organization of 1 kilo word of memory, that way reducing the decoder complexity. So, normally these DRAMs, they have typically 4 times the density of SRAM. So, this DRAM density is pretty high, and the cost per bit of DRAM storage is 3 to 4 times less than SRAM. So, this is one of the basic advantage of DRAM over SRAM. So, the cost per bit is less, and the other factor is the power requirement. So, DRAM power consumption is also low compared to this SRAM. Address multiplexing techniques, so that can reduce the number of pins in the IC package, because this what you can do. So, as I said that the total 10 bit address is divided into 2 parts, 5 and 5 bit and 5 bit. So, 5 bit row address and 5 bit column address. The address what we can do, instead of applying this 10 address bit simultaneously, we can apply 5 bit address first and then again 5 bit address. So, if I have got this memory chip and then I can have a 5 bit address lines instead of 10 bit, first I apply the row part of the address, and then after the row has been selected we can apply the column part of the address. So, we can divide it into we can divide the address part into row part and column part and apply them one after the other. So, the advantage that we get is if we have to apply 10 bit address, then this memory should have 10 address lines. So, instead of that I should have only 5 address lines and some extra control by which I can tell whether it is a row address or a column address. So, in a 2-dimensional array, the address is applied in 2 parts at different times with the row address first and column address second. Since the same set of pins is used for both the parts of the address, we can decrease the size of the package significantly. So, how is it done? We will see in the next slide. So, what is done? So, I have got a 256 by 256 memory cell array. So, initially the 8 bit address is given. So, 8 bit address is stored in this 8 bit row register, and then from this row register it goes to an 8 by 256 decoder. So, this so that way this this particular row is selected, and then we apply the column part of the address. So, the same 8 bit address lines is used to feed the column part of the address to the memory chip. So, this is giving me this is actually selecting the corresponding column. So, this is stored in the 8 bit column register, then it goes to 8 by 256 decoder, and then it selects one of the 256 alternative columns. So, this memory that we have here is 64K, sorry. So, memory that we have here is 64K. So, that is 2 to the power 16 locations should be there. So, what we have done, this 2 to the power 16 locations, instead of organizing them in a serial fashion. So, what we have done, we have organized them in 2-dimensional fashion. So, such that in each so we have got 256 such rows and 256 such columns. So, once the row selection has been done, so this row has been selected, then we select a particular column, say we select this particular column, then ultimately, so this location gets selected, and this location itself may be your an 8 bit location or 64 bit or 16 bit location, depending on the word size of the memory, but this particular memory cell will get selected. So, that way I do not need to apply a 16 bit address simultaneously, I apply 8 bit at a time, and it will be reducing the complexity in the number of pins. However, I need to tell like when I am applying the row address and when I am applying the column address. So, for that purpose, so there are 2 special pins, RAS bar and CAS bar. So, row address selection and column address selection. When I am giving the row address, this RAS bar line should be made equal to 0. So, that the value the row address is stored latched onto this row address register, and this decoder can enable the corresponding row. And then this column address, after that the column address is put, and then at that time this CAS bar line is made low, and then the value that is available on this 8 bit register is latched 8 bit address is latched onto this 8 bit column register, and then it goes to this decoder and it selects one of the 256 columns. So, that way finally one particular memory location or memory word gets selected. So, the CAS must go back to the one level before initializing another memory operation. So, that is the requirement, that first this column selection and the row selection will be done, and it must go back to 1, and then only it can become 0 again, to ensure that the operation is done properly. Next, we will be discussing about another very important topic, which is known as error detection and correction. Like when you are transferring data or storing data in the memory locations, so since the data is coming from outside the memory, so it may so happen that in the transfer process some bits got corrupted. Okay. So, the how to detect that situation and what to do, like if we see that some bits have got corrupted. So, this error detection and correction mechanisms, so they are for protecting the occasional errors in storing and retrieving the binary information. So, one possibility is the parity. So, parity can be used to check the error. So, we have seen parity separately previously, where if I have got say and 8 bit data, then I can just add another bit parity. So, I count the number of ones here, and if I say that finally I should have an even parity, then if the number of ones in this part is odd, then this bit will be turned 1. On the other hand, if this is even, then this bit will be turned 0. So, that we have seen in the XOR, and you know that this can be done very easily using the some XOR circuit. Now, this is so parity can check the error. So, it can detect the error, but it cannot correct it. So, this error correcting codes, so they can generate multiple parity check bits that are stored with the data word in memory, and that can lead to a better possible correction of the this corruption. So, we will see how this is done. So, one commonly used code for this error detection and correction is the Hamming code. So, this was devised by R.W. Hamming, and that is why it is called Hamming code. So, it is in a Hamming code. So, for n bit of data word we have got k parity bits. Okay. So, for n bit data there are k parity bits, and these k parity bits are attached with this n data bits. So, total number of total word size becomes n plus k bits, and these positions are numbered as a power of 2 are the positions which are powered of power of 2, they are reserved for the parity bit. So, it is not that I have got an n bit data and these k bits are computed and they are just attached here. So, it is not done like that, but these bits are actually inserted into the total n plus k bit. Maybe I have got one bit here, another bit, another. So, the one parity bit P 1 here, another parity bit P 2 there. So, like that. So, it says that the positions are numbered as a power of 2 are reserved for the parity bits, while the remaining bits are the data bits. So, that is how this organization is done. So, let us take an example. Suppose we have got an 8 bit data word 11000100, and we want to include 4 parity bits, and then we get a 12 bit pattern. So, this is the 12 bit pattern. Now, these bit positions are since this is a power of so this is bit position 1, that is 2 to the power 0, this is bit position 2, so 2 to the power 1. So, this is bit position 4, which is 2 to the power 2. So, at these powers of 2, so we put the parity bit. So, P 1 is put as bit 1, P 2 is put as bit 2, P 4 is put as bit 4, and the remaining bit 1 1 0 0. So, they are coming here, this is 1, this is 1 0 0, then 0 at bit number 9. So, that way it goes. And how to compute this P 1? So, this is fixed. So, P 1 is given by XOR of bits 3, 5, 7, 9 and 11. So, if you do this, the bit is turning out to be 0. P 2 is given by XOR of 3, 6, 7, 10 and 11. So, this is 0. So, this XORing pattern is fixed. So, P 4 is the XOR of 5, 6, 7, 12. So, that becomes equal to 1. So, this way this P 1, P 2, P 4 and P 8 are calculated, and once this is done, the data is stored in the memory together with the parity bit as 12 bit composite word. So, this is the thing that is stored in the memory. So, 12 bit word, that is memory. Now, when you are reading the data from memory, so you get these 12 bits, and then we check whether the parity bits are correct or not. If there is an error, then the parity bit, these parity bits will differ. So, we compute the check bits based on the similar formula, like P 1 was computed using XOR of 3, 5, 7, 9, 11. So, here we compute C 1, which is the XOR of the red values of 3, 5, 7, 9, 11. Now, if P 1 differs from C 1, that means there is some error in any of these bits. Similarly, if C 2 differs from P 2, there is some error in this bit. So, if your P 1 and P 2 both are creating if C 1 and C 2 both are not conforming with P 1, then you can say they are not conforming with P 1 and P 2, then you know that possibly there is an error in bit number 3, 7 or 11. So, this way you can figure out a few locations which may be wrong. So, how do you do a check? So, a zero check bit designates an even parity over the check bits, and 1 designates an odd parity. And since these bits were stored with even parity, the result C indicates that there is no error. So, since we have followed even parity, so if it is if this C1, C2, C4, C8 is 0 0 0 0, there is no error. But if C is not equal to 0, that means the 4 bit number formed by the check bit gives the position of the erroneous bit. So, these patterns have been selected in such a way, these positions have been selected in such a way that this property holds, that the 4 bit number that you get here gives the position of the erroneous bit. We will take an example. Suppose this is the bit that we have, this is the no error. So, this is the actual one. Now, if there is a error in bit number 1, if there is an error in bit number 1, that is this bit has got transformed from 0 to 1, but rest of the bits have not, then you will get this, when you compute this C1, C2, C4, C8, you will get this particular pattern. So, that tells that bit number 1 there is some problem. On the other hand, if there is an error in bit number 5, so bit number 5 was 1 here, it has become 0 there, and rest of the bits are okay, then after you have computed C1, C2, C4, C8, you will find that the pattern coming is 0 1 0 1. So, this identifies the bit at which the error has occurred. So, you can just flip that particular bit on the received pattern, and then you can you get the corrected version of the bit. So, this way that is the beauty of this Hamming code. So, it is XORing in such a fashion that this when you check it, so you can figure out like which particular bit has created problem. So, the Hamming code can be used for data words of any length, and total bit in Hamming code should be n plus k bits. The syndrome value C consists of k bits and has a range of 2 to the power k values between 0 to 2 to the power k minus 1, and range of k must be equal to or larger than n plus k. So, this is the requirement. So, if you using an n bit code and a k bit k extra bits or check bits, then the requirement is that 2 to the power k minus 1 should be greater or equal n plus k, then only this Hamming code will work. For example, if number of check bits is 3, then the data bits that you can that can be in the range of 2 to 4. So, if you have got a data bit of length more than 4, then 3 check bits are not sufficient. If you have got 5 to 11 data bits, then you should have check bit k equal to 4, 4 check bits will be necessary. So, this is coming from the theory of Hamming code. So, we do not have scope to discuss on that. Maybe you can look into some coding theory course which will be talking about this Hamming code in more detail. So, if you are trying to detect single error, single error and correct it, so this Hamming code can detect and correct only a single error. So, if you want to have this situation single error correction and double error detection, like as I have said that in the this pattern that check pattern that we generated was such that it identifies one particular location as erroneous. Now, if there are multiple bits which are erroneous, then this check will not be able to pinpoint to the correct error. So, it is just an assumption that in a transmission at most one error has occurred. So, Hamming code can correct it. So, but if you want to detect the situation in which if there are multiple if there are multiple bits which are wrong, so you should be able to detect it, but you may be happy if correcting only a single bit. So, single bit error correction and double bit error detection, if we are looking into that. So, for that purpose we have to add another parity bit and to the coded word. We add this word P13 here. So, P13 is connected here, and then P13 is so this P13 is computed here. So, P13 is becoming is 1 at this point. So, that is by means of taking XOR of all these bits. So, this P equal to XOR of this with 1. So, that naturally, so if you take XORs, so if P equal to 0, that means the parity is correct, even parity, but if P equal to 1, then the parity over this 13 bits is incorrect, the odd parity. So, in that case we can have different situations, C equal to 0, P equal to 0, no error has occurred, C not equal to 0, P equal to 1, so single error has occurred and that can be corrected. If C not equal to 0 and P equal to 0, then double error has occurred, it is that can be detected but cannot be corrected. If C equal to 0 and P equal to 1, and error occurred in the P13 bit. So, these are the inferences from the C and P bits. Again, it is not possible to prove these results in our class. So, you can, I will suggest that you look into some discussion on this coding theory for getting more details about this type of coding. Next, we will look into read only memory. So, read only memory, the block diagram is like this. So, we have got k input lines and we have got n output lines. So, this the number of words in a ROM is determined from the fact that the k input address lines are needed to specify 2 to the power k address or 2 to the power k words. So, 2 to the power k words are there. So, the n k bit input address is necessary, then there are n output lines from there. Now, how do you construct a ROM? So, logically a ROM is constructed like this, that each output of the, so we take a 5 to 32 decoder. So, if I have got say the 32 location ROM that we want to make. So, we take this a 5 to 32 decoder, address lines they come to this I0, I1, I2, I3, I4, and then these 32 lines are coming out of the decoder. Now, we have got these columns, and these columns are summed in the OR gates. So, each OR gate is considered is having 32 inputs. So, 2 to the power k by n ROM will have an internal 2 by k by 2 to the power k decoder and n such OR gates. But essentially whatever design that we have shown here is just a logical diagram. Physically it is never done like this, but logically you can think of it that okay, these are the components in the ROM. So, you can program the ROM like say a programmable connection between two lines is logically equivalent to a switch that can be altered to be either close or open. So, for example, we can say that say this for this I0. So, if the location, if this address is 0 0 0 0 0, at that location this is the output pattern that I expect. Similarly, at say 1 1 1 0 0, so this is the input pattern that I expect. So, if we have got separate if in this point, so we have got some connecting switches, okay, at these junctions we have got connecting switches, then those switches can be programmed in this fashion, so that it can talk about it can store the corresponding pattern that we need for the ROM location. So, this can be done by means of putting some transistors, and that will act as switch, and the transistors can be programmed to either 1 or 0. So, that the location content becomes 1 or 0.